All right, we're going to go ahead and get started for today. So I don't hear double. All right, so today we're going to be talking about Earth's oceans. We're now done with the geosphere, so we're done with rocks, the rock cycle, and we're now going to focus on all that is left on Earth, which is the ocean. Oceans cover about majority of the Earth's surface. So they're actually quite important, but we're going to go through it kind of quick. Yes, what's up? No, I gave you the papers yesterday in class. You should already have the notes.
Water composition.
Yep. Good to go?
Yes.
Okay. All right, so like I said, we're going to talk about the composition of the oceans so we get a little bit of a better idea of what our oceans are made of. Now, normally for the warm-up, I ask you guys to make a prediction about how much of ocean water is water and how much of ocean water is salt. So, Joni, you're the only one in here. What is your prediction? How much of the water, if you had to give like a percentage, what?
It's like
80% what?
80 or 70.
Percent what? Water or salt? Of water. Okay, so you say 80 to 70, 80% water, and that leaves 20 to 30% salt. Okay. And that makes sense. When we go to if you've ever been to the beach or near an ocean, you know the seawater tastes quite salty. Okay, so what we need to understand is 97% of the Earth's surface is marine. Okay, we are a giant blue planet because of all that ocean water. Okay, seawater is about 96.5% water, and actually only 4% dissolved substances. So even though we think about seawater as being incredibly salty, it's only about 3.5% salt. The rest of it is ocean water. So that shows us kind of how small the amount of salt is in seawater. So if we took a look at this, this is kind of like a graphical representation of how much of it is water and how much of it is salt. So taking a look over here. So 96.5% of it is seawater and 3.5% of it is salt. And then of that salt, this is what it breaks down. So sodium and chlorine, that's what we think of as normal table salt. So about 80%, 85% of the salt is just normal salt water, normal salt that we would put on our food. But these other metals and electrolytes and stuff are. Yes, Phoenix. Well, I'm in the middle of a lecture right now. Can you come back later? Thank you. So again, about 80% of it is table salt, and then there's some other dissolved metals and salts in there as well. Even small amounts of things like gold, there's actually gold in seawater. So, if we could mine enough seawater, you could potentially get a little bit of gold. But the problem is that gold is just part of that last 0.7. So it's so incredibly small, it would not be economical to try and mine gold out of seawater. Now, how salty the seawater is a measurement of salinity. Okay, salinity, again, measures how much dissolved salt and other solids are in a liquid, in this case, in ocean water. And we report that in parts per thousand. How many parts per thousand? So out of 1,000 parts, how much of it is water and how much of it is salt? If you take a look at the map down below, we can see that the salinity is not the same throughout the entire ocean, okay? If you look closer towards the equator, you see some higher numbers like 40, 38, 37. And then if you look closer to the poles, you see some lower numbers like 32 or 33.5. So you may already be able to think about what might be causing this to be a little bit more diluted and this to be a little bit more salty, but that's what we're going to get into. What affects the salinity of the ocean and why is it not the same throughout the entire ocean? Now, a fun little side note, there are some places where salinity is incredibly high. In fact, the saltiest body of water on the earth is called the Dead Sea. It lies in between Jordan and Israel/Palestine. And it actually is about 10 times saltier than the ocean itself. So where the ocean's only about 33.5% salt, the Dead Sea is about 33.7% salt. Dead Sea is really kind of just a giant lake now. And it's the water feeding into it has been cut off because if you know anything about that area, it's very dry and desert-like. So the people in those areas, built wells and stuff like that and pulled water from the river that was feeding into the Dead Sea. And so it literally is not getting any more water. It's just sitting there and evaporating and evaporating and evaporating. And so that makes it so incredibly salty. I'm not the most buoyant person in the world. When I was in elementary school or, growing up, we used to do swim lessons. I always struggled with floating, the back float and stuff like that. I just, big bones or something, I sink. So when I went out and I got to visit here with my buddy, he made me go into the Dead Sea, and I was like, no, I don't really want to do it. And he's like, no, you got to do it. Everyone has to sit in the Dead Sea. He's like, you're going to float right at the top. And I didn't believe him. And then I got into the water and I sat down and I shot right up to the top of the water. That is me sitting there on top of the water. It is so dense that it puts you on top of the water. There's literally people that will bring books and magazines and just kind of sit and bob in the water. And they'll read their book because you don't have to paddle, you don't have to swim, you don't have to tread water. It is so dense that it pushes your body to the top of the water because it's actually the water is a little bit more dense than you are at that point. So it is a pretty incredible experience. And like I said, it's just so incredibly salty that you just float. It's wild. All right, back to the oceans though. So ocean salinity, even though it varies from place to place, it's been pretty much stable for billions of years. This should hopefully make some sense because the water on the earth is pretty much trapped, right? Yes, it evaporates, but then it rises in the air, it condenses, it forms clouds, the clouds drop the water as rain, and then that water eventually makes its way back to the ocean. So there has not been a huge change in the amount of salt to water ratio in oceans over the course of the Earth's history. There are three main sources where the salts come from though. The first is the chemical weathering of Earth materials on land. So as that rainwater runs over land, it's going to pick up things and those that are going to get dissolved in the water like salts. And that's eventually going to be carried out into the ocean. Okay, so that's one of the sources. There's also slow erupting volcanoes all over the ocean floor, especially along that mid-ocean ridge, that divergent boundary. There are also deep sea vents that produce and release a lot of salt into the ocean. So that's another source of salt for the ocean water. And lastly, chemical reactions between the seawater and the newly formed sea rock. So as that divergent boundary continues to grow and push out new oceanic crust, that new oceanic crust is going to interact with the water, and the water is going to seep out some of those salts that it has in the rock. So three main sources are salts from rainwater and runoff on land, volcanic eruptions and deep sea vents, and then a little bit between the new oceanic crust that is created on the mid-ocean ridge. So like I said, salinity ranges from about 33 to 36 parts per thousand over most of the surface of the ocean. The overall average is about 34.7 parts per thousand. But like I said, it varies very greatly from location to location. And it all has to do with what's going on in those locations. So let's see, how does location affect salinity? Let's take a look at this. Well, the first is the latitude. Okay, remember, latitude are the horizontal lines. So it's basically saying how close to the poles or how close to the equator you are. So variations in salinity occur with latitude due to the ratio between evaporation and precipitation. How much water is being evaporated versus how much water falls out as rain, sleet, snow, or hail in that area. Okay, so we call this the evaporation precipitation ratio. So how much is being taken away and how much is being dropped in that area. So how much is being taken away and how much is dropped is going to affect how salty the water is. If evaporation is higher and precipitation is lower, well, there's going to be less water in the ocean water, so it's going to be a little bit more salty, a little higher salinity. Whereas if there's more rain falling than the water is evaporating, it's going to be a little bit more diluted, a little lower salinity. So in the temperate and equatorial regions, evaporation is less than precipitation, so it's going to be a little bit more lower salinity in these regions. But near the subtropical latitudes, near the equator, there's a lot more evaporation than there is rain, so it's going to be a little bit more salty in those oceans. So think about the equator is hot, causing more evaporation, poles are not. Okay, so that's one of the main differences in salinities in the ocean water. But that's not the only thing that affects how salty the water is. The second is how close it is to the continents. In coastal regions close to major rivers, runoff is actually going to decrease salinity. As that fresh water meets the ocean, it's going to create what we call brackish water. Brackish water is kind of very, very diluted seawater. It's where oceans and rivers and bays and stuff like that, that's where they mix. So I used to teach out in Baltimore. Baltimore is known for the Chesapeake Bay, and the Chesapeake Bay is all brackish water. There's a couple rivers that feed into it, and the ocean, the Atlantic Ocean, also feeds into it, and it kind of creates a kind of diluted salty water. We call it brackish water. However, if it's close to continents, but it's in a semi-closed area where there's lots of evaporation, then it's going to be a little bit more salty. And this is the area that we're talking about, like the Caribbean Sea and the Gulf of Mexico, the Mediterranean Sea and the Red Sea. So if we were in the room, I would kind of point these out on the map. But what we need to understand is if you look in the Gulf of Mexico, remember that's just on the western coast of Florida, all the way to the eastern coast of Mexico. That's a very enclosed area. And so there's going to be a little bit higher evaporation rates. And so therefore the Gulf of Mexico is a little bit more salty, has a little bit higher salinity than it would normally have because of all that extra evaporation. The Mediterranean Sea and the Red Sea are also in a very similar boat. They're enclosed oceans, not very big, so there's more evaporation happening to those. So they're going to be a little bit more salty as well. All right, currents are also having a big effect on salinity. So they modify the latitudinal bands of salinity controlled by evaporation precipitation by transporting salty, warm water. In our case, rather, I'm talking mostly about the Gulf Stream, but they can bring with them temperature and salinity. So if the Gulf Stream comes out of the Gulf of Mexico and up the East Coast, it's going to bring with it warm, salty water. So the waters near, let's say, like Georgia and South Carolina and North Carolina and Virginia, all up that East Coast, they're actually a little bit more warm and salty than they should be because of the Gulf Stream, that river of flowing water that comes out of the Gulf of Mexico and goes up the East Coast. We're going to focus a lot on the Gulf Stream today and this week. In the Eastern Pacific, south to north boundary currents and east to west equatorial transport cool dilute waters. So what's interesting is we're going to find that the oceans spin clockwise in the northern hemisphere. So if we take a look at a map, in fact, let me just pull up a map real quick, pull up a world map. This will do. No, I really don't want to buy anything. I just want to get a picture of it, guys. This is good. All right, so let me bring this over. Jonah, you can see that, yeah, right?
Yeah.
Okay. All right, so if we take a look at this map, what I'm talking about, so in the northern hemisphere, in this top, they go in a clockwise motion, okay? So that's why the stream comes out of the Gulf of Mexico and goes up the East Coast, because that's the way the clock moves. But on the western coast, what that means is it's coming down from the north. So the cold diluted waters from near the North Pole and Alaska, northern Canada come down. And so they make the waters around the northwestern coast a little bit more diluted. They're a little less salty than they should be because that current brings down all those diluted waters. So these were the other oceans I was talking about. So the Gulf of Mexico was a semi-enclosed one. The Mediterranean Sea, you can see, is surrounded by land. This is the Red Sea over here. Okay, also very small and surrounded by land. So any of those landlocked oceans or very small oceans, they're going to have a little bit higher precipitate, or excuse me, evaporation rate. They're going to be a little bit saltier than normal. All right, let's get back to the PowerPoint. All right. So when you take a look at the map of all the ocean salinities, the highest salinities are going to occur about 25 to 30 degrees latitude in both hemispheres. So right around the equator is what that's saying. So a little bit north and a little bit south of the equator, that's where the saltiest waters are going to be. And the lowest salinities are going to occur outside of that, 40 to 50 degrees up to the northern and southern poles. So again, those areas where there's lots more rain happening, lots more ice melting, stuff like that, there's going to be more diluted, a whole lot less evaporation. Now, seawater acts a little bit differently than freshwater, okay, because it has those dissolved salts. We call them ions because they have charges. Dissolved salts in the ocean water. They affect the properties of it. So here's some information. Not only are you going to learn about oceans and water, but something you can also apply to your everyday life. Salt affects the freezing point of water. So dissolving salt into water is going to break the hydrogen bonds that holds the water together. And this makes it makes it so that the water doesn't freeze until a lower temperature. So instead of freezing at about 0 degrees Celsius, which is the freezing point of water, that's 32 degrees Fahrenheit, it actually doesn't freeze until you get down to -2 degrees Celsius. This is why we salt the roads. Okay, in the wintertime, when it snows, you do not salt the roads to melt the ice. That's not how the salt works. But what the salt does is as the snow naturally melts a little bit, it turns into liquid water. That water dissolves some of that salt. And that salt getting that water makes it so it's not going to refreeze as easily. That's what the salt is trying to prevent. The refreezing of the snow into like ice or something like that. So that's why we salt the roads. Also, if you're at like a barbecue or something like that, and you have some sodas that you want really, really cold, or some drinks that you want really cold, and you have a cooler with ice in it, add some salt into that ice. Because what that's going to do is it's going to super cool the liquids. It's going to allow it to get a little bit colder than the water normally could get, and therefore it's going to keep your drinks nice and cool. So again, adding a little bit of salt to water is going to make the freezing point go lower, and so it can actually get colder than it would normally be able to if it was just fresh water. In addition to affecting the freezing point, salt also affects how fast the water evaporates. So salts will attract the water molecules and hold them in solution, so that slows the evaporation rate. So basically, a place you can apply this is if you're making pasta or something, boil the water and let it get to a boil first, then add salt. Okay, and yes, if you're just boiling your pasta in bland water, that's why you're eating bland pasta. You should be salting your water a little bit, okay? That seasons your pasta. So you didn't think you were just gonna learn about science in this class, did you? So again, let the water come to a boil on its own and then add some salt. Because if you add salt to it first, it's actually gonna take it longer to reach that boiling point. So again, this also affects the evaporation of oceans and stuff like that. This is why the Dead Sea is still there. The Dead Sea is not getting fed any water, so why is it still a sea? Why isn't it all evaporated? Well, the more salt that's in there, the more it holds onto the water. And so that's actually slows down the evaporation of the Dead Sea and of water in general. Salt also affects the density. Remember, density is mass per volume. So things that are more dense are going to sink and things that are less dense are going to rise. And we call water having a density of 1. So anything that's bigger than 1 is going to sink. Anything that is less than 1 is going to float. So when you add salt to the water, that's adding mass into the water. And so it's actually going to increase its density just a little bit. So salt water, if you mix salt water and fresh water, the salt water is going to be more dense. It's going to stick on the bottom, okay, because of that higher density. All that extra salt in the water adds mass and it makes it a little bit more dense. It is important to understand that temperature also affects the density of the water, and it actually has a bigger effect on the density of the water. So cold water is more dense than warm water. So cold water will sink and warm water will float. That's why if you ever dive into a pool or a pond or something like that, as you swim down deeper, you might feel the water get a little bit cooler. And that's just because the denser water is going to sink down to the bottom. Now, this is only true until about 4 degrees Celsius, because after that, the water begins to freeze. And we know when water freezes, it expands, that spreads it out, and that's going to cause it to become less dense. That's why ponds freeze from the top down. You ever wonder why that happens? Remember, as it gets colder, the water gets more dense, so it's going to sink. But then as it gets down to about 3 degrees, 2 degrees, 1 degree, and then 0, when it begins to freeze, the water molecules actually spread out and form sheets of ice. And that's why it freezes from the top down, because that as it spreads out, it becomes a little bit less dense. That's why it rises to the top and freezes from the top down. Fish and aquatic life would have a very, very, very hard life or big problem if water froze from the bottom up. So it's actually really good for them when it freezes from the top down. And like I said, temperature has a greater effect on density than salinity does. So the most dense water would be very cold salt water. Then we would have maybe room temperature salt water. And then we would just have probably room temperature, or excuse me, cold water. Those densities would just slowly get lower, less and less and less as you got to like fresh water. Warm fresh water is the least dense water. All right, this is just a graphic showing us the different densities of the densities and salinities of the ocean. We don't really need to understand this too much, but what we can see here is in some areas, the Pacific is a little less salinity, lower density than the Atlantic Ocean. The Atlantic Ocean is actually a little bit higher density and higher salinity, but we don't need to understand all of this. That's okay. The Arctic Ocean, that's very, very cold water. That's the most dense. That's why that's down there. Okay. Lowest temperature, decent density. Okay. All right. So what we can see here, this is a map of the world's oceans and seas. So some of these, we have North Pacific, South Pacific, North Atlantic, South Atlantic. There's the Indian Ocean. You may know about the Mediterranean Sea. There's the Black Sea. There's the Red Caspian Sea. Red Sea's in there as well, right down here. We've got, this is part of the Pacific Ocean, so that's part of over here. We've got the Arctic Ocean, and then the Southern Ocean, which is south of Australia, Africa, and South America. All right, what you guys have left for today, the next thing I'd like you to work on is an article. Go ahead and pull that up. You've got a reading with some vocabulary, excuse me, with some vocabulary words. Yeah, the readings are just the next page. I'm pulling them up separately. So here's the reading, okay? I've highlighted where the vocabulary words are. So as you read through, what you're gonna do is using this chart, you're gonna use the word, I give you a sentence, I give you a picture, and you're going to come up with a predicted meaning for what that might mean. You can also use the reading to help you come up with a predicted meaning. So you're going to read through this. There are some questions at the end of it. Okay, where it says paragraph, please write me a paragraph. Don't just write me a sentence or two. Okay, so we got 5 questions, and then you have the vocab words. It is front and back, but there's only I think 7 words. So it's really not that long. So come up, as you read through, come up with a predicted meaning for each vocab word, and then answer the questions after that. Okay. And then all you have left is the exit ticket. I think that's all we have for today. That's all I put in that packet, right? Just the reading and the vocab. I just don't have it in front of me. I believe that's all I put there. So go ahead, read the article, answer the questions, and fill in the vocab chart with predicted meanings. Any questions? All right. Well, I'm gonna hop off the Zoom, so thank you for Zooming today. Like I said, if you have any questions, please let me know.